Alright then, it's time to make a sequel to my Z490 Dark unboxing and overview video. So let's make a BIOS overview and check out all the features inside the motherboard's BIOS, and then do some like practical overclocking tests and check out all the different aspects that you have to take into account when you overclock with this motherboard. So we get into the BIOS by selecting the advanced configuration or the Ender setup from these four options over here, and so we can see on this nice graphical UI that we have Intel Core i9 10900K, CPU at 3.7 GHz, CPU temperature 26 to 27 degrees Celsius. The VID of this CPU is 1.01 volts roughly. 16 gigabytes of memory, so I'm using 2 sticks of Kingston HyperX Predator 4133 Cas19 sticks, and well, they are pretty much the same, or actually a tiny bit better than the Galax Hall of Fame OC Lab 4800 MHz Cas19 sticks, which I showed you briefly in the unboxing video. So the stock XMP, or like the stock setting what memory kits often have, it doesn't guarantee how well they will overclock. I've seen many very high memory bins that really suck in terms of overclocking. Like I had one G-Skill 4400 MHz kit that was really bad, but then on the other hand, my original G-Skill Trident Z 3600 1616 has always been wonderful when it comes to overclocking, and I used that kit in all of the top scores I made on the Z390 Dark when it was coming out to the market. So I just wanted to stress out that the memory kits, just like CPUs and so on, they really differ a lot in quality, so they do vary a lot. So do not expect to get the same results as some other user if you buy exactly the same memory kit. But yeah, so in the first tab we can find all the overclocking settings for the CPU and memory controller, like all the voltage settings, the CPU core and cache ratios, base clock, and so on. In the extras, so if you stay in the OC tab and you press left arrow key once, you will highlight the extras, and then if you press down arrow, you can see all these different options over here. Currently, as this is a beta BIOS, there's still no OC profiles added, but they will be integrated in the public BIOS, so stay tuned for them. There will be very handy BIOS profiles for you to use to overclock your CPU and Samsung BDI based memories on air or water cooling, and even on LN2. So there will be different profiles for the two different BIOS, or I mean the PCB revisions. So for the older PCB type that generally likes to do 4133 to 4200 plus with 12.11.11, and for the new A2 PCB action at 4800 Cas14, and for daily wise there will be high frequency one, so 4600 to 4900 stuff, and a more generic like 4000 to 4300. That's generally possible even with both PCB standards, although the newer A2 PCB is generally much better in daily configurations, no matter what frequency range. But yeah, so you can use on the Z490 Dark BIOS, the same features do exist as on the Z390 Dark. So we have the stress test function, we have the OC robot, so the automatic OC feature, and then we have the BIOS update as the bottom option over here. I have not really used these these features myself, so the stress test or the OC robot, but they should work somewhat okay to some degree. But of course, I will show you how to overclock this whole motherboard and rig manually, because that's what this motherboard is truly all about. So, first tab is about OC. So when we select the CPU multiplier control from auto to manual, we will open up the CPU overclocking options. So we have individual multiplier for all of the cores, so all of the 10 cores plus overall setting. So if you want to overclock all cores at the same frequency, you can just use this one over here. But if you want to give different multipliers for different core count loads, you can do that with these settings here. So for example, if you wanted to set like 5.5 gigahertz for one core workloads, or like one and two, like single and dual core workloads, you can do that. So now the CPU would have 5.5 gigahertz overclock for any workload that only uses one or two CPU cores. And then we can have lower multipliers like 5.4 for workloads that use 3 to 4 cores, and then we can have like lower multiplier for like 5.2 gigahertz setting when CPU uses more like 5 cores or more. So this is quite handy. This would be the most ideal way to overclock daily wise, to really find out like max performance in every situation. But it's much easier to overclock all of the cores at the same time, at least for like primary testing. So but this also depends a lot on your cooling solution. So for these CPUs, because the 10 core is the most highlighted CPU part of this whole like Comet Lake 10th gen launch, the 8 core and 6 core models, they are actually often worse than the previous generation chips. Generally, the 8 and 6 core CPUs, they don't overclock as well as the top bins from the previous generation. So the 8 core model is actually overclocking worse quite often compared to the 10900K and the 10900KS of the previous gen. And the same thing goes for the 6 core. So the 6 core Comet Lake is actually often worse than the absolute best 8700Ks and the 86Ks. So just saying. So if you buy the Z490 Dark, I would really expect that you will be getting the 10900K with this board, because this board is not ultimately like the cheapest motherboard model in the whole like Z490 lineup. It's not the cheapest one, so it's more at like the higher end models. So definitely not the cheapest one. So I really expect you will be getting the 10900K this board. But yeah, so cooling solution is what matters the most when you start to overclock these CPUs. So if you are unsure, you definitely should get like a very strong all-in-one water cooling with good thermal paste, of course, like Kimping Cooling KPX, the new Cryonaut or Cryonaut Extreme or Gelid Solutions GC Extreme or something like that, to get the best possible temperature performance, or even like custom water cooling loop. I'm using a very strong custom water cooling loop in this example over here with Kimping Cooling KPX thermal paste. But if you are unsure, you can, like if you have some like simple air cooler, like strong air cooling tower like Noctua NHD15 or D14, you can start at like 4.8 gigahertz across all of the cores. And well, generally 4.5 cache will always work. 4.5 is nearly the stock setting for the cache, so it's very certain that this will work if you use at least like 1.2 volts on the CPU. AVX ratio offset, or the negative offset, is very important setting with these CPUs as well as on the X299 CPUs. So with this option you can give a lower CPU multiplier when the AVX instruction sets are being used. So in this like example, so if we start at 5 gigahertz, we would have this 5 gigahertz speed in any workload that doesn't utilize the AVX instruction sets. And if we use an AVX ratio offset of 2, it would drop the CPU frequency to 4.8 in all of those workloads where the program would utilize those AVX instruction sets. So with this feature we can make sure that the CPU remains stable in every situation, because the programs that can utilize those AVX instruction sets mean that the CPU will draw more power, because the AVX instruction sets allow the CPU to work more efficiently, but it results in higher power consumption and therefore in warmer temperatures. So if you run, let's say, like 60 degrees in non-AVX workload, expect the temperature to be like 70 to a bit over 70 in AVX based situations. And it also depends on if it only uses AVX1 or even the AVX2. AVX2 will draw even more power than the AVX1. But generally, like a good option on the AVX ratio offset is 2, like 1 to 3. Generally, the max frequency for AVX workloads will be 100 to 200 MHz lower than in non-AVX programs. But I would generally use a value of 2 here. Then base clock, easiest way is to leave it at 100 all the time. Extreme voltage mode is mainly for LN2 situations, but if you want to do some really tough memory testing on air or water cooling, and you want to run higher memory voltage than 1.6 volts or higher system agent than 1.55, you need to enable this. It is safe to enable it on its own, so it doesn't set any voltages higher automatically by itself. It only allows you to use like higher range on those voltages. So, but the only use case scenario on air or water cooling where you have to enable this is if you run some like heavy memory testing, like 4800 MHz CAS14 action with 1.95 volts on the memory, or like 4133 plus with 12, 11, 11 timings with 2 volts on the memory. Those are two good example scenarios for this. LN2 mode, yeah, only enable this if you run the CPU on LN2. You actually don't even have to enable this if you only use like dry ice, single stage, or even cascade. Generally, you only have to enable this if you go colder than -120. That's just my personal experience. Now VCore. Generally, it is easiest way to overclock the CPU with fixed voltage. So adaptive would be the most ideal. So with adaptive, it will lower the CPU voltage on idle, but it's at least for like primary testing, I would use the override option. So fixed voltage across every workload scenario, and the target voltage or the value where you would start. It all depends on how good your cooling solution is. If you want to start at like 4.8, if you have some like air cooling unit, then I would recommend you start with a VCore value of like 1.15 to 1.2. But as I already know my cooling solution, so I have a very strong custom water cooling, I will use a value of 1.3. But do not start with any higher value than 1.3. Generally, you can a good value to start with is like 1.2 to 1.25. VCore V-droop, there are many options here, but generally the best option for daily use is the -25 less droop. This is very spot on with the set value. So if you set 1.3, it will be at 1.3 on idle, and with this option over here, the voltage under load would be like a very touch over the set value, like 1.304, 1.305. So very spot on with the actual set value. So use -25% on air or water cooling, and on LN2 I recommend you set -50%, because on LN2 the loads are higher, and therefore even with -25 there will be some droop. So the voltage will be under the set value under load, and there you should use -50%. But for air and water cooling, -25% is the best option. VCore PWM frequency, as the Z490 Dark, just like the Z390 Dark, has very overbuilt VRM, you should want to get some faster transient response. So I recommend you use the max option, so the 800 kilohertz on the VRM. It should help the stability a tiny bit, but it's really like small thing overall. It's very likely you don't see any difference between 300 or 800 kilohertz. The only thing you might see is touch warmer VRM temperatures, but will not matter with the Z490 Dark because it's so overbuilt. But use 800 over here. V-core guard band, generally you don't have to touch. Then there are mainly those like PLL voltages for LN2 use and so on. But one big thing for memory overclocking compared to previous generations now is the system agent voltage. So all until now, I generally said that you should never go beyond 1.4 volts on the system agent and I/O. But with the Comet Lake CPU, the scaling on the system agent is actually very good, and it's safer to use higher values than before. So now it's pretty much safe to use even 1.4 volts on these two, even for daily use. And we have been running the system agent at the max value, so at 1.65 volts for many weeks and months, almost like non-stop, when doing like really hard testing with the board to test all the functionalities and so on. So you can use even 1.65 volts on air or water cooling for testing purposes, and I'm not kidding. Now we actually saw one CPU dying from very like prolonged use of 1.65 system agent, so there is some risk involved. But for like brief testing, for memory testing, you can use 1.65 volts on the system agent, even on air or water cooling. And on LN2, if you want to run really hard MEMS like 4800 plus, 14, 13, 13 with command rate 1, you need to set 1.65 system agent. But 1.4 is very safe for like normal use now. So it's very good feature about this new CPU. So much safer than before. But other than those two, you don't really have to touch these. VCC, PLL OCs, standby, these are only for LN2 use. On air or water cooling, you can leave them all at auto. So that's pretty much it for the first section of the BIOS, so the OC tab. So the next one is the memory. But one thing I will, because I will start at 1.3 volts, I will set 5.2 across all of the 10 cores and 4.8 on the cache. But that is just for my CPU. Every CPU is different, you have to test it out yourself. But actually many CPUs can do 5.2. I mean, of the 10 core CPUs, they can do 5.2 at least for Cinebench with very good water cooling. But just saying, but every CPU is different, you have to test it out yourself. But the next tab is the memory. So the easiest way to run good memory settings is to load the XMP of your memory kit. So the XMP of this HyperX Predator kit would be 4133, 1923, 2345 and so on. And the XMP of the Galax kit would be 4800 MHz, 19, 26, 26, 46 at 1.5 volts. But memory overclocking is much harder than CPU overclocking, especially with the Samsung B-die based memory. Samsung B-die based memory is quite hard to get fully stable with the entire capacity. So you might be able to pass something like LiDAR, like SuperPi 32M, HyperPi 32M, and even like Prime 95. That I think it was the blend part that stresses memory as well. But the best way to truly test out the stability of your Samsung B-die based memory is to run something that stresses the entire capacity of the memory you have installed, like HEI memtest, Lynx, the part of Lynx that stresses the entire capacity, and I think there are even like newer memtest programs out there. And memory overclocking is very hard. These memories can easily get more unstable if you run too high memory voltage. I will give you a good example soon, but you have to find the correct settings, like even the best voltage value for your kit and your timing configuration. If as an example, if you are, let's say, unstable at 1.45 volts, it could be possible that you will be fully stable at 1.4 volts. So increasing your memory voltage doesn't always give you more stability, so just saying. So like I will give you a good example now. I was doing daily testing with the memory frequency range of my daily profile of my Z390 Dark. So like the daily profile of that board was 5.2 GHz CPU at 1.3 volts, and memory frequency of that timing table was tuned for 4 GHz to 4300 plus, and it had 4300 statement in the BIOS. But I was doing like daily testing and with 1.45 volts and with 17, 18, 18 timings, and I always failed at around like 50% of HCI mem test. But then I used the same frequency of 4200, but I dropped the memory voltage to 1.4, and I also tuned, or I tightened the main timings to 16, 18. Oh wait, I had TRAS at 32, but it doesn't matter. I lowered the main cast timing from 17 to 16, with many of the sub timings set manually, like 4 active window of 23 and cache write latency of 16 and so on, and it was fully stable. The problem with XMP profiles is that it only sets the main timings plus the frequency, and all of the sub timings will be crazy loose. So if we look at this, so 45 TRAS is very loose. We can run this at like 32 or even 28, and like 4 active window 44 is very loose. This has a lot of impact on performance. A good value on this will be like 23. 23 is easy to run. You can sometimes even run like 16, and it sets, this is an important one, so it sets the TRFC to 725. The XMP profile of my Galax OC Lab kit sets this at 880, and I often when I look at the very high megahertz bins, like 4800 megahertz kits, the XMP profile might set the TRFC at 1023, so over 1000. This is a very loose setting, and the TRFC has huge impact on performance. It's one of the most important memory timing settings after the main timings. Like the most important sub timings after the main timings are like 4 active window, cache write latency, then TRFC, and then the last two of the third timing. So the TWR underscore DR and DD. These, the best option for these is usually 4. You can set even lower than 4, but it generally makes the performance worse. So 4 on these two is generally the best. But I will set like a good daily configuration right now, and it will be included as a profile as well. So I will set this to manual. I always use manual when I set things myself, so I don't like to use XMP, because sometimes if you overclock manually with XMP enabled, like you set timings yourself, the performance might be different compared to if it was set as manual. Even if all of the timings are set manually, there might be a performance difference compared with manual and XMP. So I always recommend you use manual if you set all the things yourself. But let's set that 4200 megahertz right now. But this timing table, which I will set, is generally good for like 4000 all the way up to 4300 plus. But again, it depends on your memory kit, and every memory kit is different, and there are huge like list of options you can buy from. But generally, if you buy a motherboard like this, I would expect you buy a really good Samsung BDI based memory kit, like G-Skill Trident C4000 CAS 15, or even of the higher megahertz pins like 4400, 4600, 4800. But I wouldn't expect you will buy some 2666 CAS15 stuff or something like that. That's really like low end for a motherboard like this, but that's just my personal opinion. But yeah, so 4200, 1.4 volts. Dim VTT is a funny setting. Some memory kits might gain if you lower this. So the standard settings will be DRAM voltage times 0.5, so 50% of DRAM voltage. So when I set 1.4 over here, the dim VTT will be set to 0.7 on its own. And some memory kits might gain if you lower it. So if I set like -50, then it would set the dim VTT at 1.65. I mean 0.65. So 0.7 minus 50 millivolts. So that would be 0.65 volts. But you have to test it out yourself. I generally leave it at auto because it seems so like rare where you actually can gain from it. But that's just my own experience. Then the main timings, I will select 16, 18, 32, and the main timing, I mean the XMP kit of this kit was 4133, 19, 23, 23. So we are increasing the frequency, but we are also lowering the timings. So that's like win-win situations. We make the bandwidth higher, but we also make the kit more responsive by lowering the timings. We will leave these at auto. I will select 4-active window to 23. Cache write latency to 16. I think even 14 would be possible, but I will select it at 16. So same as cache write latency, I mean the cache latency itself. Then command rate 2. What I've seen so far is that the difference between command rate 1 and 2 is actually quite small. So you can generally get much higher frequencies if you leave the command rate as 2, and that will like bypass the gain of command rate 1 if you can get much higher frequency by keeping the command rate as 2. But you can use command rate 1 as well if you want to try. And if you stay at this frequency range, you could aim for command rate 1. And that's what I also tested with these kits, actually with both of these kits. So I had the command rate as 1. But you can leave it at 2 if you want to, and 2 is easier. But generally, if you leave the command rate at 2, you should try for some of the higher like frequencies. Write recovery time can be like 10. TRFC, that was very high on the XMP profile, but generally you can easily get like 360, even at 400 megahertz. And you can even lower it to like 300, but under 300 starts to be very difficult. So I would recommend you use like 360 over here. T-refi, or the reference interval, is the only setting that differs from all of the other options, is by that the best performing setting on this would be the maximum one. So the max option, so 65,000 is the strongest setting you can use on this one. But generally for daily you can leave it at auto. The best on these would be 1 and 6, but it might be quite hard, so you can leave them at auto as status. And TCKE, I usually like to set this myself. Best option is 4 on this one, and good value is generally like 4 to 6, so I will set it at as 5. These can be left at auto. They usually set them they usually set to good values or relatively good values on their own, but these I might want to put manually, so I will set to like 9974444 because we want these last two at 4, and these can run even at 4, but it might fail in the first attempt if you set them very tight at the start. Then all of these other options we can pretty much leave at auto. RTL is quite important. It really depends on like luck. Do they set to good values on their own? You can increase the risk or the chance that they will be set to good values by increasing the IOL offset to 22 from 21. So but it really depends. You can leave these at auto if you want to, but sometimes I like to set these at 22 to improve the chance that they will be set to correct values, because sometimes the RTL might bug. It might set the first channel to 56, but then the second channel will be like 69 or 71 when it should be 57. They should be close to each other if they set themselves correctly on their own, but just saying. But yeah, so that's for the memory part. And then we can move on to the advanced tab. CPU configuration, we can find all the CPU features like virtualization, hyperthreading, C-stage, but generally you don't have to do any changes over here when it comes to daily use. You might want to set the debug LED monitoring feature yourself, but that's generally the only thing you might want to change. For testing purposes, if you are familiar with the famous 3D Mark test called 3D Mark Vantage for DirectX 10, it was released with Windows Vista, like during Windows Vista days in like 2008. That test is a very good example of this option over here, so per core hyperthreading. So 3D Mark Vantage has a very famous CPU test, and it can only use up to 16 threads. So you will not gain at all if you have a higher core count than 16. So 16 core CPU would be the most optimal one, and you would then run the CPU as 16 cores but without hyperthreading. So 16 cores, 16 threads. And the 10900K has 10 cores, 10 physical cores and 20 threads with hyperthreading. So we have 4 threads that will not be used by the test. So if we want to maximize the performance for 3D Mark Vantage, we want to have the hyperthreading running on 6 of the best threads. So with the per core hyperthreading, we can disable the hyperthreading from 4 of the worst CPU cores, and then we would run the CPU as 10 cores but 16 threads, and we can get slightly better, or we could get a slightly better overall CPU frequency with 10 cores and 16 threads than 10 cores and 20 threads if the last 4 cores clock worse than the other of the core, than the other cores of the CPU. But this is something you have to test out yourself, and it's only for those like extreme overclocking situations. But that's the one of the main differences compared to the previous generation. So you can actually disable the hyperthreading per core. But when it comes to daily use, you generally don't have to touch this at all. But that was just one of the use cases where you could utilize this option. That comes to my head. But generally, you can just leave these at auto for daily use. Graphics configuration. Here you can disable the iGPU or the internal graphics, and you can select the primary display to PCI Express or the graphics card, but again you might not even have to touch these at all yourself. PCI Express, you can select different generation to each of the PCI Express slots, but again no need to touch these on when it comes to daily use. For special overclocking scenarios where you would have to touch these is if you run some older generation that needs older PCI Express generation to get better temperatures. A very good example is AMD Radeon HD 7970 or the 280X. That one has bad code bug if you run the newest PCI Express Gen, so the Gen 3. If Gen 3 is being enabled, you will face a code bug with 7970 at around like -50. And if you set the PCI Express Gen to 2, so instead of 3, you can go much colder in temperatures, like -150, and then you will get better frequencies overall. So that's like one of the only cases where you have to touch these, like get better temperature on a graphics card. But that was just one of the only use cases, again, that came into my head. But for daily use, you can leave these all at auto. You don't have to touch these at all. PCH only says what versions you are running, like ME version and so on. Power management, don't have to touch these at all once again. Onboard device configuration. Here you can disable the internet or the LAN and even the audio, and you can even disable the M.2 ports and so on. But again, for daily use, you don't have to disable anything. USB, you can disable the legacy USB support, but again, no need to touch anything. SATA, you can choose between HCI and RAID. And with the BIOS version that supports Windows XP, you can set IDE to the AS Media SATA ports. Now the important one, or the only important option over here, is the hardware monitor configuration. Here you can choose what thing you want to monitor with the onboard debug LED. You can even rotate the monitoring from normal to reverse, but again, you can choose from many options over here what you want to monitor with the onboard debug LED. So by default it will be monitoring the CPU temperature, but it's not very well, it's quite accurate. The figure, when you monitor the CPU temperature, the figure will be same as the CPU package temperature, and package is usually the same as the hardest core. So it's like the CPU temperature in worst case scenario. But generally what I like to monitor with this is the VRM temperature, or the PWM, but you can choose from many options over here. So we can monitor the CPU temperature, the VRM temperature of the CPU. I think the system temperature is some spot somewhere around the motherboard, but it's not very accurate. It's not like it's not any like important value, so I don't see any reason why you would monitor this one, because it's at 16 at the moment. It's some it is some spot somewhere on the motherboard, but not sure where. Maybe near the rear I/O, but I'm not fully sure. The ADX6P is the supplementary PCI Express 6-pin power connector. Then we have both of the M.2s over here. So if you want to check what's the M.2 temperature, you can choose between these two. We have the memory voltage VRM, so the memory VRM temperature over here, but doesn't really it doesn't really run warm. This one doesn't really, this is not true at all. The temperature in my room at the moment is 21. It cannot be at 9 degrees. But you can monitor the memory VRM if you wanted to. Then we have the PCH, or the temperature of the Z490 chipset itself over here. Then we have different voltages, so we can monitor the V-core voltage at the hardware level. So if you don't have a multimeter at hand, you can check. If you want to test the different load line calibration options, or the V-droop options, you can use this feature over here to check the V-core under load with different load line options. So you can use this, but and it's quite accurate. It's very spot on with the with actual multimeter measurement. But so you can monitor the V-core voltage, memory, VCCIO, VCCSA, standby, VCC PLL, PLLOT, PLLOC, and VTT postcode, and you can even turn it off completely if you don't like it. But generally I like to monitor the VRM temperature, because that's like a secret risk that many people don't take into account with many motherboard models with different platforms. So I like to monitor the VRM temperature of the CPU myself. But that's pretty much it. Nothing in the trusted computing, and I don't have an M.2 device plugged in at the moment, so we don't have anything on the NVMe option or part of the BIOS. And boot, if you are installing Windows 8 or newer from a USB stick, you have to select the boot mode select to UEFI. So for example, if you install Windows 10 from a USB stick, you need to have this at UEFI. If you install operating system like Windows 7 or even a newer one from a DVD, then you have to select this at legacy. Like you install Windows 7 from a DVD, you have to set this at legacy, or Windows XP, Server 2003, Windows Vista, or even 8.1 from DVD, you have to select this at legacy. but we have Windows 10 at the moment that's installed from a USB stick, so we have to keep this at UEFI, and we can find hard disk, Windows boot management or boot manager over here. And here you can choose the drive if you have multiple drives installed that you wish which one you wish to boot. But yeah, and then over here we can save changes and reset. We can load defaults. We can boot override some specific drive, and here you can save your profiles. You can save profiles to the BIOS chip itself and even to a USB device. And here I already have many options over here, but you have many empty spots to which you can save a profile to. But yeah, so that's pretty much it. That's how the BIOS looks like, but it's pretty much spot on identical with the Z390 Dark BIOS. So generally you will not find any differences whatsoever, but the biggest difference really is the range on the system agent that you can select now. So you can go much higher on the system agent than before, safely I mean. So let's press F10, so save and exit these settings, and let's see how this thing performs in the operating system. Okay, so this is how the operating system looks like. There are a couple of programs which I would download in your case, and I will of course link them all down below in the description box. But we have like CPU-Z for overall validation, so we can see which speeds we are running. So right now we have a 10900K, 10 cores, 20 threads at 5.2 GHz across all of the 10 cores. This voltage measurement isn't correct on the Z490 Dark. It was the same on the Z390 Dark as well. And this CPU is actually not the same one I used in the 5.5 GHz Cinebench run. This is a slightly older revision, so this is stepping, or well, revision 4. The stepping and revision is like upside down, or they should be the opposite ones. So this is like the revision 4. The one I used in the 5.5 GHz run was stepping 5 or revision 5, but this is also a quite good one. This can do 5.3 in Cinebench very easily, and 5.4 is on the edge. It will pass when the CPU or when the ambient temperature is relatively cool, and if I delete the CPU, it will surely loop 5.4 easily, and maybe even can get close to 5.5. But yeah, so this is the CPU. So where CPU Z 1.9 2.2, but of course I'm sure there is already a newer version available. Main board is Z490 Dark, but this is a better version, like for testing purposes. And in the memory we can see DDR4 16 GB, so 8 GB per stick. Dual channel cache is at 4.8, 4200 MHz, so 2100 DRAM frequency, and DDR stands for double data rate. So 2100 times 2 is 4200 MHz, 16, 18, 18, 32, 360, common rate 2. And SPD, you can see the correct, I mean the stock values of your individual sticks. So Kingston, HyperX 4133C19, blah 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 blah, and the stock XMP profile over here. So that's pretty much it. Then for temperature measurement, I really like core temp. It's very small, so it's tiny. It doesn't consume system resources that much, and it's very easy to use. So it's not like huge list of different values like hardware info or hardware monitor. But that's just my personal preference. You can use whatever temperature measurement program you wish, but I really like core temp. Then Elite X1 is the new Elite to change all the settings. You definitely have to get this one, and this gives correct voltage readout. So we have VCore 1.291, DIMM 1.4. The Z490 Dark actually overshoots the memory voltage by 30 millivolts. So we set 1.4 in the BIOS, but we can see 1.435 over here. So just saying, but 30 to 35 millivolt overshoot isn't that bad, or it's not anything dangerous, if you ask me. System agent, we have small overshoot once again by 20 millivolts. VCCIO, we actually have 20 millivolts of droop, quite funny. No, we set 1.35, so we have 30 millivolts of overshoot. PLLOC, standby, these are for extreme overclocking, but yeah. And we have the overclocking functions over here, so we have multiplier adjustments for all of the cores individually, cache or the ring, and base clock. So you have to get the Elite X1. It actually works, so it's much better than the Elite versions that we had previously. They had a lot of bugs and it often didn't even work. So definitely get the Elite X1. I will link it down in the description down below. Then you can use Cinebench for like pre-testing, because it's very fast and it gives you like rough idea of your stability. So if you get Benchmade is very good. It has many of these tests integrated as one pack. So we have Cinebench R11.5, R15, R20, and so on. So but you can get Cinebench independently as well if you wish. So let's open R15. R20 is a bit harder. It uses some AVX instruction sets, so it's the same, but R15 is completely non-AVX. Then to really test or verify your daily stability, you have to get Prime 95, and this is the newest version. With the newest version, you can choose like non-AVX workload and different AVX workloads, so AVX1, AVX2, and so on, and even AVX 512 with the X299 CPUs. But that's pretty much it. ASRock timing configurator is very handy to check all of the sub-timings. So now we can see which settings it set on its own, because we didn't set everything manually. So we can see it set these rust to rust delays at 12.9. We left these at auto. 18.12 were also left at auto. We have 4 active window 23, which we set manually. RTLs are pretty much okay. 61, 61, 7, and 6 on the IOs. This is not the most this is not the tightest option at this frequency and cache latency, but they are all right. And we have the last thirds as 4.4, which we wanted to get. These are quite tight for this configuration, so 12, 12, 12, 12. These are okay, but not the tightest options, but they are okay. So this is quite good configuration overall. But to completely verify your memory stability, you have to test the entire capacity, which I already said. So HEI memtest is good. Links, the feature in links that stresses the entire capacity, and or even some of those newer like memtest programs. But you have to test the entire capacity. HyperPi gives you like good rough idea of your stability, but it's not enough to completely verify the stability of your entire memory you have installed in your system. But you can use like 32M, and well, this only goes up to 16 threads, but it's already quite hard to pass on its own. But let's check now. So we set 5.2 because it depends on your cooling solution what you can start with. So again, if you use just some air cooling, you should use like 1.15 to 1.2 VCO and 4.8 GHz. So let's run Cinebench R15, and we can see that temperatures don't even go past 60 in my example over here, and it seems to run 5.2 quite well. The minus is the VCO, as we don't see it. We don't know what it was under load now. We can open Elite to check the VCO value under load. So look over here, so 1.29 roughly. But you have to, if you really want to see the accurate value, you have to use a multimeter. So from those Probit connector heads, let's run it again. So it went up by 5 millivolts. So at around like 1.3, so spot on with the set value and the load. That's why I like the -25 droop option for daily use. But very easy to pass, so now we can try to go even higher on the frequency. So 5.2, so we can select 5.3 across all of the 10 cores. We will hit, just double check that nothing is set incorrectly over here. So they are what they were. And override mode 1.3 volts again, so it doesn't accidentally go to adaptive, and apply. And boom, we have 5.3 across all of the 10 cores once again. So let's run our 15 again. And still roughly the same. The temperature will go up slightly when you... Oh! And it crashed. So we have to try again. So it's on the edge. So now we have to just increase the V core. So that was actually my bad, because I forgot which CPU I'm running. So the better CPU can easily run 5.3 at 1.3 volts. But so like a good example, I will show you over here. So you can easily test with Elite. So let's say you initially try at 5 GHz with 1.25 set V core. So let's actually do that. So let's set CPU to 5G and V core to like let's set 1.28, but it could be 1.25, and apply. 5G now on CPU Z, and V core reads 1.274. You can easily use this to quickly test your CPU. So now it runs at 5 GHz. Temperatures will be very cool, like mid-50s. But again, really play like cautiously. So proceed with caution, because the temperatures can be very warm with some CPUs if your cooling solution is not good. So now that we passed 5G, we could go up to 5.1 across all the cores again and run again. 5.1 across all of the cores. Temperature slowly starts to creep up, because when you increase CPU frequency, the amount of amps that the CPU draws will also go up. So voltage is not the only figure that affects the overall temperature, the overall temperatures and power consumption. The CPU frequency itself will also impact the overall power consumption and heat. And now again, 5.2. I think this should pass even at 1.28 volts. But it starts to be on the edge. But this one will pass 5.3 at like 1.34 volts or 1.33. Did pass 2811. So now let's set V core to 1.34 and CPU speed to 5.3. Now it measures 1.329. CPU Z 5.3. Run again. Now temperatures are going up a little bit. 64 warmest, 65. Like 62 average at the moment, I think. But I already know this CPU, so the maximum non-AVX speed this CPU can do on all of the 10 cores is 5.3. It can pass 5.4 if the room temperature is quite cool. But that's very on the edge. So this CPU could probably do like 5.4 to 5.5 in single and tool code load, and 5.3 in full 10 core load in non-AVX workloads, and for AVX like 5.1 to 5.2, and that is the spot where we will utilize the AVX negative offset. So I will quickly try the 5.4 for you, but I will not try it for multiple times because it's very on the edge. and the operating system has to be very light for that thing to pass. The cache really doesn't matter if it's at 4.7 or 4.8 or even 5.2. It has very small impact on your performance. It's like the number 3, like third most important factor when it comes to overall performance. The most important thing for performance is the CPU core, then the memory, and then the cache. And we are not talking about 3D performance, because that's of course where the graphics card is number 1, and then you already know it. But when it comes to like 2D performance, cache actually has quite small impact on overall performance. I don't even try to maximize the cache fully myself. So you can also try the cache after finding the max you can do for the core. But we can leave it at 4.8 and 5.4 now, 1.395. The scaling with these CPUs once again goes really bad after 1.4 volts. There's absolutely no reason to use more than 1.4 on the V core. You will not gain any stability on normal air or water cooling. And it even starts to go bad after 1.35. So that's why I generally like to stop at around like 1.35 when it comes to daily use. The scaling from the V core is very good under 1.3 volts. If you can do like 5.1 with 1.2 volts, then you can do 5.2 with 1.25 volts or 1.24. But then if you do like 5.3, in my case 1.33 volts, 1.4 might need 1.4 volts, or it doesn't pass at all, no matter what voltage we try with. So after that we can only get better frequency by getting the CPU temperatures cooler than the ambient room temperature. So that's the overall story when it comes to CPU overclocking with these CPUs, all the way since the Skylake CPUs pretty much. So 5.4, 1.395, apply. It measures 1.385, CPU Z54 across all of the 10 cores. We can disable this. And this is very on the edge, so it might pass if we close core temp, and it might crash if we leave it at open. But let's just try, but I will not try it for many times in a row, because there's no need. So you can see, so it crashed to desktop at around like 30%, and max temp was 70. It will not go much warmer than 70, but if it stays under 70 on all of the cores, it should pass that test at this voltage. So we could try it quickly in real time, just purely out of interest, because if you run this in real time, it's slightly easier to pass, because it doesn't use the system resources to any other like background process when you run this in real time. But I think it will fail. See, the circle starts to move, so it crashed. But very on the edge. We can try one more time. But as you can see, it's very on the edge. No blue screen at least yet, but it really is on the edge. But if we deleted the CPU, it would pass this like constantly. Deleting with direct die should improve the temperatures like 7 degrees, maybe close to 10. But that's so 5.3 is our max speed for all of the 10 cores now. But I'm sure you got the rough idea now. So that's what I was doing with that 5.5 GHz run. I was trying it on at real time with that same voltage, because it was so on the edge. But this would pass. If we tried that like 10 times, it would pass, I'm sure. But there's no point to try that, because we cannot get it stable in like fully normal situation across all of the 10 cores. But now, what we can try is, now you could try to hunt like daily stability at 5.3 in non-AVX situation, even across all of the 10 cores. So we can set this at 5.3, same cache, and let's put 1.35 volts. Could be even like 1.36. Apply. And I want to show you the AVX instruction set as well. So let's open Core Temp plus CPU Z. Put it over there. CPU Z. Now Prime 95. The latest version. Just stress testing. Now I generally like to run in small FFT, but you can even use the smallest FFT. And we will disable all of the AVXs, so you can disable AVX one by one. So we can disable AVX2 and even the AVX1. If we had Skylake X or Cascade Lake X, so X299 CPU, we could even disable AVX512, 2 and 1. So let's try to run small FFT in non-AVX mode, see the temperatures, and does it run at 1.35 volts. So not that much warmer compared to Cinebench. So this would be the way to determine your non-AVX stability across all of the 10 cores. So from our Cinebench testing, we can confirm that we can obtain 5.3 GHz overclock on all of the 10 cores in non-AVX stability. 5.4 was very close on passing, but it will not go, especially during like summertime when room temperatures are very warm during the day. But we can hunt for 5.3 stability, but this depends on your CPU itself. So if you have better CPU than this one over here, it could be 5.4. On the other chip I used in the 5.5 GHz demo, we would be running 5.4 at this very moment. And then with the AVX ratio offset or the negative offset, we can use like 200 MHz lower speed for AVX scenarios, and we can try that soon. So I would recommend you run this for at least 1 hour, maybe a few hours, and see if it's stable. If it crashes, you need to increase the vCore to like from 1.35 to like 1.375, and I'm sure you should be able to get this 5.3 GHz overclock stable. But again, if you really want to maximize your performance, you should use the per core overclocking function. So with this CPU, 5.3 for all of the 10 cores in non-AVX, 5.1 with all of the 10 cores in AVX scenarios, and like 5.5, maybe even 5.6, but like 5.5 for single and dual core, then 5.4 for like up to 5 or 6 cores, and 5.3 up to 10 cores. So you get the idea, I'm sure. So you would just have to let this run. I'm not fully sure what the end temperatures would be, but I think probably close to 75. Now the thing with AVX is that it will increase the temperatures by quite a bit. We cannot actually see the watt figure with this Core Temp version. So let me close that one. I will check if I can get a newer version right now so that we could see the power draw figures, because it would be handy for this demo purpose. Okay, so now I updated the Core Temp to 1.16 version, and we can see that we are running around 300 watt load without AVX. So I think these are actually quite good temperatures, considering that the power draw is 300 watts. But that's really one of the reasons why you really have to keep in mind what cooling solution you are running. So a CPU like this, 10 core on a mainstream platform, you should have at least like a very strong AIO, like with a 360mm radiator, or a very thick like 280mm one, or even a custom water cooling loop like I have in my case, because these do get relatively warmed, but these are cooler by default than the 10900Ks, because the CPU die thickness is thinner or lower than before. So that actually gives you that gives us better temperatures at same power consumption levels than before. But yeah, so 5.3 without AVX, and now let's stop this and let's stress with AVX, because remember we set AVX ratio to 2, so -2. Let's see how it works now. So torture test, and let's try AVX1 first. So we will disable AVX2, so we will only run, because look, AVX, AVX2, so let's only run this part of the AVX right now and see if it drops to 5.1. So now we have 5.1 gigahertz running, and temperatures already went to like mid-70s. Maybe the average is actually like 73, a bit over 70. So we are still staying under 75 on average, I think. Power went to 325.5, but I'm not fully sure how accurate this thing is actually in like reality. It could be more than just, the difference could be more than just 25 watts, but I'm not sure. Let's open eLead X1 so we can see, or we can confirm the figure. 1.30 set, 1.350 set, measured 1.353. So very spot on. So now you get the reason why I told you to use -25% small V droop. If we used -50%, which is also a good option, this would be 1.375 or so, like 25 millivolt overshoot. Okay, so temperature difference was already like 7 to 8 degrees between non-AVX and AVX1. Sadly, we don't have a ratio negative offset for different AVXs, so we could use like -1 for AVX1 and -2 for AVX2, because the AVX2 is tougher than the AVX1, so the AVX2 will run even warmer than the AVX1. So let's see the temperatures now with AVX2. So torture test, small FFTs, and we do not disable either of the AVXs. Let's see, do we crash or will we remain stable? Actually quite small difference. So actually the biggest difference is jumping from non-AVX to AVX1. So if it's so yeah, then there's definitely no need to have separate jump between the two AVX revisions. On X299 the reason is much more clear, because there are just so many cores. So the differences will be larger because of the core counts. So yeah, you can get a rough idea on the temperature difference. So maybe 10 degrees overall between non-AVX and AVX2. So good negative offset is 1 or 2, not more than 3. You definitely don't need more than 3. So, but I would use 2 just to be safe. And to test your stability, you should let this to run once again for a few hours. But the VRM temperatures do start to creep up. Well, you cannot see it right now, but as I put the PWM measurement on the onboard debug LED, it's currently measuring 46 degrees Celsius, and I have some airflow coming from the 24-pin side of the motherboard. So keep an eye on the VRM temperature when you let this running. So you should put the PWM or the CPU VRM temperature as the measured target value on the debug LED. And you can of course use your fingers or your hand or like a laser thermometer to check the temperatures at the VRM area. But definitely keep an eye on the VRM temperatures, because on some low-end motherboard models the VRM definitely gets warm when you let something like this running for longer periods of time. But that's how you overclock the CPU. Definitely use the AVX negative offset and use the per core function if you want to get the most out of your CPU. 5.5, like you can get 200 MHz with single and dual core loads compared to 10 core loads, and well, you get the idea already, I'm sure. So that's how you overclock the CPU. Memory, when it comes to ultimate memory performance, the key is to find the best sweet spot between frequency and timings. This is already a very good configuration in itself, but it loses to this loses to 4800 megahertz frequencies, even if the timings are quite significantly looser, like 18, 24, 24. I have some screenshots over here for you, but we can try. A good way to measure performance is to run the ADA64 bandwidth test on the memory, but it only measures the bandwidth. So in this test, frequency is king. So this is not like a real world test. A real world test is to run a good real world test is to run something like Geekbench 3 or Geekbench 4, or like just simple game tests. That's better way to see the like real memory performance differences between different configurations than this. But this is like a good a good way to test, at least somewhat. So we will get some figures on the top line over here. So read speed will be, you can see dual channel DDR4 4200. CPU speed also affects these figures. So it actually runs this at 5.1. If it seems this uses some AVX, it seems. 61,560, 62,854, almost 57,000 on the copy, but this ruins my testing because the other figures were run at 5.2 GHz without AVX offset, and latency was 39.8. But I have some figures over here. So this is stability proven with these memory sticks at this memory configuration. So we have 4200, 16, 18, 18, 32 command rate 1, same subtimings pretty much. Entire capacity is being tested, so 98%. Multiple HCI mem test executions running because I don't have the paid version, so I cannot run the entire capacity in single execution. And oh wait, this is different screen. What is this? This is same. This is another test as well, but yeah, you get the idea, I'm sure. I should have one performance test somewhere over here. So here I have stability proven again with same memory sticks at 4800 megahertz, 18, 24, 24, 36, 360 command rate 2. Many subtimings are the same, so we have 23 command rate, 23 for active window, cache write latency of 16. 16, 16, 16 on these 4 and 4, 4. Actually, one thing I forgot to mention on this one, we have command rate 1. So I actually validated command rate 1 with this exact same timing configuration. So you can try command rate 1 if you stay at this frequency range. And this timing table is very good for memory frequencies from like 4 GHz all the way up to 4300 plus. But you have to play around with the memory voltage. And it depends a lot on your IMC as well, because the IMC quality differs a lot on these CPUs. Some CPUs might not do 4800 MHz memory at all, and some CPUs will do it easily with quite low system agent. So let's see if I have some figures over here. This is hold on a minute. This is 4800 CAS 18, same profile confirmed on my Galax OC Lab kit. So I've confirmed it with 2 independent memory kits with same CPU. And hold on a minute. This is memory bandwidth test at 4800, 18, 24, 24. So 66,410, but this is now, this was run at 5.2 without the AVX offset. So this one should be like 63. Actually, we can test it right now. We can run it again. We can run it quickly, so we don't have to boot again. 5414, because I don't want to reboot. So we can look like side by side. So see, 52 over here. But it does, the CPU speed does impact the memory bandwidth as well. So it was 60. Oh, like no difference whatsoever. But it will impact the memory bandwidth to some degree, but not that much compared to the actual like memory frequency and timings. Frequency is king for these three figures over here, and latency is impacted greatly by the memory timings themselves. Good latency is like below 40 nanoseconds. So 39.7. Let's open up this screen one more time so we can put them side by side. So this is 4200 16, 18, 18 compared to 4800 18, 24, 24. Timing, the difference in main timings is quite huge, but the frequency is also 1600 megahertz higher over here. 66,410, just touch under 61k, or it was 61.5k on the previous run. 71,000 compared to 63,000. 61,600 compared to 56.5k. Latency is pretty much the same. So the higher frequency compensates the difference in the timings. So we can determine, at least based on this test, that this configuration over here is better than the 4200 16, 18, 18. So you don't have to fear too much about the timings getting relatively loose with the high megahertz pins, because the high bandwidth really compensates the jumps in or the steps in the main timings. But you have to keep the sub timings at reasonable values to get this good latency figure. So even on this run, so on the 4800 megahertz run, we have TRFC at 360 instead of 1023, like 1/3 of the XMP figure. We have cache write latency of 16, 4 active window at 23, last thirds at 4/4, 16, 16, 16, 16. This could probably be even at 12, 12, 12, 12. So yeah, so I'm sure you get a very good idea right now what is good, like how to overclock CPU and memory. But these are mainly like my personal points of view about overclocking in general. If you watch some like mainstream YouTube kings like Chase Ducents, Linus, they might have different options and ways to overclock CPU and memory. But this is like my way of running the things. But good real performance, like real world performance indicator is like Geekbench. Geekbench is very handy, and something like just game tests. Game tests where CPU performance has big impact as well, like Far Cry 3, Far Cry 4, they have huge impact. I mean, they get huge impact from CPU frequency and memory when graphics card is not bottlenecking the situation. Like running Far Cry 4 with very high-end graphics card at 1080p. That's a game test where you will see big differences from memory, I can tell you. So let's wait this test to finish, and we will get a memory score, and we can see how good it looks like. Dijkstra is the hardest spot to pass, so you will generally fail at this part if it fails at all. At least when it comes to memory. The hardest spot for CPU is the DFFT. But yeah, I will have, or EVGA will have 4200, I mean, well, 4000 to 4300 profile with these main timings and command rate 1. If you stay at this frequency, you should try for command rate 1. And if you run very high frequency, like 4800 megahertz or even above, you need to run command rate 2 pretty much. And now we passed the score, 51,744. Memory score 7606. Not that bad at all. Not that bad at all if you ask me. But yeah, that's how it looks like. That's how you overclock the CPU, cache and memory on the Z490 Dark. Very straightforward, same as before, same as on the Z390 Dark and so on. So if you like to see this demo, then please give a thumbs up. But again, to completely verify CPU stability, you have to run Prime 95 a few hours in non-AVX mode to determine the non-AVX stability, and a few hours in AVX mode to test your AVX negative offset, that are you running high enough negative offset. And then memory, you have to test the entire capacity of the memory you have installed. You have to test 16 gigabytes if you are running 16 gigabytes, and you have to test 32 gigabytes if you are running 32 gigabytes of memory. So I can't stress them more than enough, because really Samsung BDI has weakness that the higher the capacity you stress, the more unstable it becomes. So definitely, I mean, test them completely thoroughly so that you don't get some weird crashes when you do like video rendering or some other like heavy duty tasks and so on. But yeah, so give a thumbs up if you like to see this video and subscribe to my channel. And other than that, thanks for watching once again, and I will see you on the next one.